आज का टॉपिक हमारे पास जो रहेगा, जो जेई मेंस और एडवांस और +1 के हिसाब से भी बहुत इंपॉर्टेंट है, दैट इज़ रिलेटिव वेलोसिटी, रिलेटिव मोशन रादर। और रिलेटिव मोशन की बात कभी भी हम करते हैं, सो वी ऑलवेज मीन्स विद रिस्पेक्ट टू वेलोसिटी। तो रिलेटिव मोशन या रिलेटिव वेलोसिटी में हमारे पास द इम्पॉर्टेंट थिंग इज दैट reference frame is one of the important concept of the relative motion. It's called as a reference frame. So reference frame is nothing but the platform or the position of the observer. Reference frame is position of the observer. If the position of the observer changes, the entire scenario is going to change of the velocities. So we are going to take two cases. In the first case, let us say that there is a vehicle and on this vehicle this is moving with the velocity of VA, and this vehicle has a long platform, and on this platform a person is moving with the velocity VB. In the first case, the observer is stationary and it is standing at this position. This is the observer. So the velocity observed by this observer with respect to the person, we can say that velocity of person B with respect to, let us call this as C, with respect to C will be equal to VB plus VA. This is the relative velocity with which the observer C will be able to see this B person will be moving with the velocity of VB plus VA if they are moving in the same direction. This was our first condition. Now in the second condition, let us write it this way, first condition. Now in the second condition, the observer, that is C, is moving in this direction with respect to velocity Vc. Now observer itself is moving, so for this condition second, we can say that the relative velocity VBC will be now coming as VB plus VA minus VC. So we can see if the reference frame in the first case was stationary, the velocity, relative velocity, will be coming as this first equation, which is based on that observer is stationary. And in the second part, if observer is itself moving with the velocity Vc in the same direction, then the equation suddenly changes. So it means the position of the observer or the reference frame very much define what will be the velocity of the person or the thing which he is observing. From this question it is very much clear. Now the relative motion have two very important applications. First is, we can call it as a river flow case or swimmer case, sometimes it is called as. So case 1, we can call it as a river flow case, or it is also called as a swimmer in the river, swimmer plus river case. So in this case, let us consider that this is the river and it is moving in this direction with the velocity uf, and the swimmer jumps from point A in this direction and it wanted to reach point B, but because of the flow of the river it continues to travel in this direction and reaches point C. So if we say that the swimmer wants to go in this direction in the direction of AB with the velocity V, but what happens, because of the flow of the river it reaches a point C. So actual motion direction will be AC, and the direction it wants to travel is nothing but AB, and this is called as a drift. This is called as drift. Okay. So in this case we can say that due to the flow of the velocity drifted along the river by a distance BC. Okay. So we can complete this. So this will be our VF and this will be the velocity of the swimmer. Let us call this as VR. So VR will be the velocity of the velocity of the swimmer because of the drift that is produced because of the river. So we can find out the components of the velocity. Okay, we can find out the components of this velocity. So we can write that components of velocity of the swimmer along of the swimmer. Let's write it here. First part is along the flow of the river, along the flow of the river. So along flow of the river, that is, you can say, let us call this as x direction and this is called as y direction. So we can say that v of x will be nothing but equal to u of f in this direction, and second part, perpendicular to the flow of the river, perpendicular to the flow of the river, we can find out v of y will be equal to v. So we can find out the resultant, that is Vr, net velocity, can be given by the velocity triangle, which we have already drawn. So we can draw this here also. This is uf, v, and this is our vr, and we already found out its horizontal component as well as vertical component. So we can say that vr will be equal to uf square plus v square, that is x component as well as y component. Now if d is the width of the river, okay, for d be the width of the river and t is the time taken to cross the river. So we can say that as the swimmer is swimming across rather in the direction AB, so only one component of the velocity, that is Vy, will be affecting the time t. So we can say that this implies that swimmer crosses the river with velocity Vy. So it means the time taken t will be t divided by Vy, is only, in this case, the component Vx rather, we can make a comment here that velocity Vx is only used to drift, motion. It doesn't help in the crossing the river. So it means that our time t is only dependent upon the Vy. So we can also find out what will be the drift, that's the distance traveled because of the drift. So we can see that this has the distance because of the drift. Let us call that distance as x. So x will be equal to drift speed into time taken. Okay, so drift speed is nothing but speed of the velocity of the river. So it is uf, and time taken is, we already found out, is dy by v. So we can say that x, that is a distance because of the drift, is given by the speed of the river, the width, and the velocity of the swimmer. In the second case, rather the same thing but in the opposite direction. So we once again consider this a river, and it jumps from the point A. Let's draw the normal. This is point B, and it goes into angle of theta with the vertical, and ultimately it reaches point C. In this case V, and once again UF is the velocity of the river, so this will be our UF, and we can clearly see that this will be our resultant velocity. Okay. So in this case also, let us write this same thing here. The swimmer jumps from the point A, into the river, making angle theta with the vertical. Here vertical means normal to the current, normal to the flow of river. So in this case, net velocity, so you can see that net velocity of the swimmer with respect to earth, net velocity of the swimmer with respect to earth. This will be coming as, we write this as V net it will be V plus UF. Now we can find out the components like we did in the first part, velocity component along the river. So we can find out velocity component, along the river. So let us call, okay, this is our x direction and this is our y direction. So we call this Vx. We are going to get this as UF minus V sine of theta, because the component of V is in this direction and it is making angle of theta with the vertical. So this component will be V cos of theta, and this component will be coming as V sine of theta. Okay, that's why it is coming as V sine of theta with a negative sign. Next is velocity component in the direction perpendicular to the river. Velocity component perpendicular to the river. So we can write Vy, it will be equal to V cos of theta. Now again we find out the net resultant component, or we can simply say resultant velocity with which swimmer will cross the river. Resultant velocity with which swimmer will cross the river. And we can write this VR. This will be equal to Vx square plus Vy square. And the time taken by the swimmer to cross the river. Time taken by the swimmer to cross the river. So if it is represented as T, so we can say that T is D divided by Vy. So we can write D divided by Vy is V cos of theta. And in this case also, we can find out the drift along the river. Drift carried along the river will be given as x is equal to Vx multiplied time t, and we already know Vx, so we can write that x is equal to uf minus v sine of theta, and t we already found out, that is given as d divided by v cos of theta. This is the drift. Okay, now we can make a slight, you can say, changes in the expression. We once again consider a case. Let us say that this is the river, this is our x-axis and this is our y-axis. Now the swimmer is wants to go in this direction so that it reaches point A, but because of the river velocity it follows this path and reaches point B. Okay, so if you call this as velocity of the river VR, and so the net, this will be coming as VR at an angle of theta. Okay, so we can write this as same thing but in a different way of representing. Now the swimmer is neither perpendicular nor it is going in upward direction, but it is always in the downward direction so that it reaches point A, but because of the velocity of river, that is VR, it is able to reach point B. So in this case, this AB will be called as a drift. So we see that OA, this is point O, OA is the initial direction, of motion of man, and OB is the actual direction. OB is the actual direction of motion of man. So because of the velocity of the river VR, what happened? The swimmer reaches the point B. Okay, so we can write this as when swimmer, here swimmer is nothing but man, reaches point B, its x component, x component is given as x, and d represent the y component, d represent the y component of displacement. So in this case d will be the y component of the displacement, that is the width of the river, okay, and x will be the x component. So we can find out the, using the coordinate system, we can find out Vs with respect to water is given as Vs cos of theta I plus Vs sine of theta j. Okay, so Vs is nothing but the velocity of the swimmer or man. So we divided this into two components. One is in the x direction and another one is in the y direction. So in the next part we find out the velocity of the water with respect to ground, and that will be equal to Vwi, because it is traveling in the only in the one direction. Okay, so in this case Vw is nothing but velocity of the river. So we can find out Vsg, the velocity of the swimmer with respect to ground. Velocity of the swimmer with respect to ground will be equal to Vs cos of theta plus Vw times I plus Vs sine of theta to j, because velocity of the swimmer as well as velocity of the water are in same direction. It is, that's why it is coming as addition of these two things. Now from here we can easily find out the x component of the velocity. X component of resultant velocity. So we can write that Vsg in x direction will be equal to Vs cos of theta plus Vw. This will be the x component, and we can also find out the x displacement component that we already said is represented by x. So we can find out x displacement component, and this will be given as x will be equal to, in x direction multiplied by time t. So we already know VSG with for in x direction, it will be coming as Vs cos of theta plus Vw multiplied by time t, and we can find out y component of displacement also. You can see that y displacement component we call this as simply y will be equal to velocity in y direction, that we already know is Vs sin theta multiplied by time t. Next we find out the time. So we can say that time taken to cross with the width d. You can say time taken to cross the river width, which is nothing but d. So in this case we can say that y nothing but d. So this time t we already know will be given by d divided by the y component of the velocity, that is Vs sin of theta. We can write it here also, t is equal to d divided by velocity of y component. So if we substitute the value, we are going to get the answer. Okay. In the second case, now we are going to say that it moves in the opposite direction, and that case will be same as the second case which we already discussed. Okay. If you want to draw, we can draw the diagram also in different way. Here let this be x and this be y. In this case also it starts from in this direction and wants to reach point A, but velocity of the river is in this direction. Okay, and let's draw a normal here, but because of velocity of the river it reaches point B, and this is the theta. So same case but in a different way of representing, but ultimately the result will be coming as same. Now there is another important application of this relative velocity that we can call as the case of the rainfall. That will be the case of rainfall, and it is same with respect to the relative velocity. Okay, so we can call this as rainfall cases. Rainfall cases. So in this case, if we say that the velocity of the rain is given as VR, and velocity of man is given as Vm, then the velocity of the man with respect to velocity of the rain with respect to man. So we can say that velocity of rain with respect to man will be given as Vrm, and this will be equal to Vr minus Vm. and we can use this for various cases. In the first case, we say that the rain is falling at an angle of theta with the vertical. So rain is falling like this, and it is making an angle theta with the vertical. So we have to find out the position at which it is going to hold the umbrella. Basically, this is the question. So in this case, let us say that the man is the man, okay, and it is moving in this direction with the velocity Vm, and rain is falling in this direction. Let me draw this one. Rain is falling in this direction with the velocity Vr. So we are going to use the triangle law to find out what will be the relative velocity with respect to, okay. So in this case, Vm, the man is moving with the velocity Vm, and rain is falling, making an angle of theta with the vertical. Okay, so we are going to find out what will be our Vrm. So we are going to use the triangle law. Vrm is in this direction, and Vr is in this direction, and it is making angle of theta. Okay, man, let us complete the triangle law. Minus Vm, so the resultant will be Vrm, and it will be, let's draw a dotted line, and we are going to get this will be our Vrm. So we can say that the man should be holding its umbrella in the direction of this resultant. Okay, then only it will be able to keep itself safe, or we can say dry. This was the first part. In the second part, we consider, in this case, let me write it here, that rain is falling at an angle theta to the vertical. Okay. Now in the second case, rain is falling vertically downward. Rain is falling vertically downward. So it means now rain is falling in this direction. Vr. So this is our Vr, and the man is traveling in this direction with the velocity Vm. Now once again, we are going to find out at what angle, okay, at what angle with the vertical should the man should be holding the umbrella. Suppose this is the umbrella, and let us suppose, and we are going to find out at what angle this person will be holding. Let us call this as a phi angle. Okay. Now again, we are going to draw the triangle. The velocity of the rain, that is Vr, is falling in this direction. So this is our Vr. Vm will be completion of the minus Vm. So the resultant will be given by Vrm, and this will be the angle phi. Okay, so this should be the position of the umbrella. So if the rain is falling vertically downward, we simply complete the triangle by taking VR, that is the actual velocity velocity of the rain, and the velocity of the person, man, so that it completes a triangle, so it will be coming in the minus direction. Or we can also represent this in the form of the triangle also. So this is our VM actual, but in order to complete, so we need VM in this direction, so that our triangle is completed. And VR, we already know, is in this direction, so this completes the coordinate. So with the help of coordinate system also we can represent it. In the next case, we consider that find the velocity with which the car is moving, so let us suppose this is the car and it is moving in this direction with the velocity Vc, and we say that and it has to hold a umbrella. It's an open car basically. Okay, you can see that this is open car and it has to hold an umbrella that it keeps itself dry. So let us suppose this is the vertical and this is the position of the umbrella. Okay, and the rain will be in this direction. So let us call this as VR. So rain is falling vertical downward, okay, and car is moving in this direction from left to right. So in this case, we find out same case but in a different way, that rain is falling vertically downward with velocity VR. Car is moving with velocity Vc. Okay, so we are going to find out its resultant. So let's complete the triangle. So we have, this is our VR and this is our Vc in this direction. So we are going to get a resultant in this direction, that will be minus VRC. Okay, so we can say that VRC is equal to VR minus Vc, or in this case we can find out Vc, what is the velocity of the car. So Vc will be equal to VR minus VRC. Okay, so this is the almost same case, but in the different way a little bit. So this completes the two cases. First was the swimmer case and second was the rainfall case. In the next, we are going to consider some of the questions or numericals based on the relative velocity, which includes both the rainfall case as well as the swimmer case. Thank you.